Since this is the first afternoon talk for you guys after lunch, so I hope you are asking a lot of questions to stay awake. So what I'm going to talk about is distributional modeling of molecules, conformers, blind docking, and molecular design. And this is quite recent work from our group in the last conference and forthcoming conference. So just as a sort of a very general motivation, proteins obviously are important units in understanding how molecular systems or cell works, protein activity, protein-protein interactions, dysfunction of protein activity or interactions are major underpinnings of diseases, including cancer. So often we wish to modulate protein activity or their interactions with small molecules. And since, say, protein-protein interaction interface, when two proteins bind together, that interface is quite large in comparison to the small molecule that you're trying to modulate that interaction with, it's very important to understand exactly where it binds in that interface, kind of targeting the hotspot residues, rather than just knowing that it binds somewhere in that protein. So one problem that I'm going to focus on today is blind docking understanding. If you give me a structure of a protein and a small molecule, just a 2D graph of your drug, where does it actually bind on the protein? Now, to solve that problem, you also need to understand drugs themselves. They are quite flexible, typically, as molecules. So you need to understand the flexibility of them and their preferences in terms of taking binding poses. So I'm going to start talking about learning molecular conformers, low energy configurations of drug-like molecules, and then taking that understanding to the blind docking problem. Now, similar techniques can have, and we have as well, used for also molecular design, not just taking sort of pieces that we already know, protein or a small molecule, and seeing how they interact, but actually generating new molecular matter, whether you're designing an antibody, how it binds to an antigen, designing a binder for small protein or nanobody therapeutics, or scaffolding a known binder into a smaller form to be more therapeutically accessible, or designing small molecule drugs. So similar techniques can be applied to these problems as well. And I'm in particular going to talk about the scaffolding problem here. So I'm going to start talking about modeling small drugs, trying to learn to generate low energy conformers, then moving to blind docking, and ultimately to designing small proteins, scaffolding known binders. All right. So what is the problem that we are trying to solve with conformers? So you are given here a 2D graph of a drug, and you wish to generate an ensemble of configurations, conformers, that have low energy, okay? And we're going to use machine learning to solve that problem. So in some sense, the algorithm will need to understand or derive some understanding of the physical principles that lead to those configurations based on examples, okay? So where do we get the examples? Rafa, who is at the workshop, has actually generated a data set of fairly small but still reasonably sized drug-like molecules, a couple of 100,000 of them, solved them via metadynamics. So we have an ensemble of ground truth, what I'm going to take as ground truth, conformers for each molecule. Now, that's the ground truth. As the drugs get larger, it's very hard to perform these calculations, so it's actually useful to learn a model to generate them. You could use cheminformatics tools, essentially rule-based methods for generating these low-energy configurations, but they don't work quite as well. Now, to solve that machine learning problem, mapping a 2D graph to a set of low-energy conformers, people have already tried machine learning methods for that problem, including ourselves. Our first method tried to assemble local structures together to create those 3D conformers. A later approach essentially transported methods from computer vision to try to solve this problem by viewing a molecule just as a point set of atoms, their locations, adding noise to create a noisier and noisier version of that, and then learning the steps to denoise those noisy samples. So applying a diffusion model to generate point sets as approaches. All right, and we'll see that actually the more geometrically guided version that I'm going to present next works uniformly better than these faster than physical calculation alternatives. All right, so we're going to focus on only the essential degrees of freedom. So we're going to drastically reduce the number of degrees of freedom that we have to optimize over in order to generate these conformers. So we take the 2D graph, we use an RDKit package to create the local structures. So you get an atom bond lengths to its neighbors and bond angles. That's what I call a local structure. And those tend to change much less than the torsion angles, the rotations along the rotatable bonds. So I'm going to only modify the torsion angles. So we're going to reduce from large number of degrees of freedom to only degrees of freedom in terms of these torsion angles. And that gets us most of the way there in terms of realizing these conformers. But there is a subtlety now because we take these local structures as fixed. We cannot actually necessarily reconstitute all the examples that we see in the training set. So there's a little bit of a discrepancy. So the first thing that we do here, this is just an illustration of changing the torsion angles, what kind of structures you can get. What we do here as a first step is we take a calculated low energy configuration and we find the closest match that we can get to by changing only the rotatable bonds. Okay? And we use these close matches as the... Excuse me for a second. We use only the closed matches as training examples. Unfortunately, my voice may be going away, but hopefully it lasts at least a little longer. So now we have a training set of these closed matches. We learn to generate them, generate a distribution of them. And at test time, we're going to compare our generated conformers to the real calculated conformers. So this close match issue is gone at test time. We are just using them during training. All right, so how do we solve the generation task? So the only things that we change are these torsion angles. So we essentially have a geometric problem. If you think of having just one angle to change, the relevant geometric object is a circle. If you have two angles, you get a torus because you can change two. If you have multiple angles, torsion angles to change, you get a hypertorus. All right. So a point on this hypertorus corresponds now to a molecular conformer. Okay. So what we are trying to reconstitute or learn to reconstitute is a distribution on this hypertorus. Okay. And we're going to learn that using a diffusion process. So we're going to first define a process of adding more and more noise. So going from a real conformer, low energy conformer, to a random configuration. Okay. And we add just noise on this hypertorus geometrically. That's just a wrapped Gaussian. And ultimately, as you add more and more noise, you are sampling from a uniform distribution over this hypertorus. Okay? So you can add more and more noise, and then you learn a process to reverse this. You're learning a model to denoise a noisy version of compound here, successively denoise, and get a sample of an actual low energy conformer. All right. So now when we actually solve this problem, we don't actually operate directly in this hypertorus. We actually operate in terms of the actual molecular configurations. And the reason is that we want a representation that generalizes to varying numbers of angles that we need to change. Molecule changes, it has different numbers of torsion angles to change. So it's actually easier to find a generalizable solution by operating directly in terms of the molecular configurations. All right, so what do we need to do? You start from a random configuration here that corresponds to a particular configuration. Then we need to generate an update for each of the possible rotatable bonds of how to denoise it, and do this successively. Okay, so that is the model that we learn, and you can get training examples for this process easily by starting from a real conformer, adding noise up to some level here. Now you know how much noise was added and exactly what that noise was, and we can then learn to reconstitute those steps by predicting corrections to the torsion angle. All right, so that's a geometrically placed or embedded diffusion process that we are learning. All right, so now how do you test whether your generated configurations are actually good? Remember, we have examples of new molecules that the model has not seen, and an ensemble of low energy configurations for those. So we can test both recall and precision in terms of our generated sample. So what recall here means is that if I generate a set of samples, then for each of the true conformers, low energy conformers, can I find a sample that I generated that's reasonably close to the one, to the real one? Okay, can I cover all the real modes of configuration? And precision is looking at each sample that I generate, does it actually fall very close to one of the real conformers? Okay, and in terms of these metrics, this geometric diffusion over the hypertorus as a way of generating these conformers is actually uniformly better than the alternatives, which are the RD-kit version commercial packages, as well as the previous machine learning methods. All right. So now we have some understanding of how to learn to generate interesting poses for drug-like molecules. So now we're going to take that understanding and try to solve a harder problem, which is what I call blind docking. And what that means is I am given a 3D structure of the protein and a 2D graph for a compound, okay? And I wish to predict the 3D pose of that compound relative to the protein where it actually binds, okay? And it's blind docking because I'm not giving you any additional information about where it might typically bind, say a binding pocket within the protein, okay? So now, how do I measure if I succeed? You have crystal structures of complexes of a protein and a bound ligand. And now I can compare, for example, based on root mean squared deviation of how close my pose is to the ground truth example that I have in the data set. All right. And typically in these type of evaluations, it is enough to get the binding pose close enough so that I can, say, score the methods based on the fraction of times across the data set where they make a pose prediction that's at least, say, within 2 angstroms in terms of RMSD, at most 2 angstroms away from the real structure. All right. So how has this problem been solved before? The traditional approach is via so-called search-based methods that essentially decompose into a search algorithm and a scoring function. And you try lots of millions of different binding poses of the compound, and you can score each one and rank them and take the best one, okay? So it's quite heavy computationally, but still actually generates state-of-the-art accuracies in terms of the RMSD or the fraction of times that the candidates they generate are within at most 2 angstroms of the correct one. For these methods, knowing the binding pocket actually helps because it reduces the amount of search that you have to do. And this is just a list of typical search-based methods. And in the same order, I have here a little bit larger the methods if you're interested. All right. Another approach is to learn this, learn to make those pose predictions. And the main advantage of that has been speed. There are deep learning approaches are considerably, typically orders of magnitude faster than the search-based methods. However, they have not yet attained the same level of performance or accuracy here. And the red bars here correspond sort of in the order of time, equibind, tank-bind, and E3 bind, 3 deep learning approaches in terms of their accuracy relative to these standard search-based methods. Okay, so they are orders of magnitude faster, but haven't yet achieved better performance. All right, so how do we approach this problem? So we're going to turn this problem into a distributional problem. And I should have contrasted here before that the deep learning approaches that have been tried previously, I would classify them as regression methods. And the reasoning is the following, that given the protein structure and the ligand, they make a prediction, typically a single prediction of the binding pose, and compare that to the ground truth, and then propagate the error backwards. So that is like a glorified regression problem where the output is the binding pose. And this formulation actually has some consequences that we are trying to avoid by casting the problem in a distributional manner. All right. So we do distributional modeling on two levels. One is the ligand pose itself, independent of the protein, as well as its location on the protein, the actual binding pose. And we already talked about the first one, and now we are going to extend that to add additional degrees of freedom, which is the translation and overall rotation of this ligand so that you can find the binding pose on the protein. All right, so let's do a few steps here to argue why distributional characterization or reframing of this task is actually useful. Okay. The first reason is an obvious one. There are actually multiple possible strong binding locations of these ligands on the protein. So you want to generate those as candidate samples rather than essentially focus on a single one. Now, the effect from the regression is actually a bit subtle one. And it has some adverse consequences if you're trying to predict the binding pose with the regression methods. And you can think of it maybe in a simpler way as follows. So if you think of a 1D regression problem, you have x-axis here, the covariates, you have y-axis here, the outcome. And if the covariate information isn't sufficient to make the prediction, there are other confounders that you're not measuring, then the outcomes might have multiple modes there. Okay. But if you're estimating a regression model, what it tries to predict then is the mean of that rather than finding the real modes. Okay. And this effect actually happens with the previous deep learning approaches. Here's one example. So here are two modes. This is the correct one, but the regression-based deep learning method generates a binding pose in the middle, which is exactly what you don't want. You would want to cover these likely modes. Okay, so distributional characterization here, even with the limited covariate information, is actually a good way to frame the problem. Another consequence here is that if you don't model the ligand preferential poses of the ligand itself, you are liable to making predictions about self-intersecting configurations. And this also happens with the other deep learning approaches. The last reason that I'm going to highlight here is that getting the answer a fraction of time correct, it's actually very much tied to a likelihood of getting the prediction correct. So it also matches this distributional view. All right. So how do we solve this problem as a distributional prediction? So you're given ligand as a 2D graph, your drug, you're given a 3D structure of the protein. And what we do is solve this as a diffusion process. So first you randomize the initial location, orientation, and the torsion angles of the ligand, and then successively denoise that pose towards an actual sample of a real binding pose. Okay. Now, you generate few samples, and then we also introduce a ranking confidence score here method that evaluates those poses and allows you to pick the best one. Now, the number of poses that you evaluate is very small, say, or on the order of a few tens, rather than the millions that you have in a search-based method. So the confidence score method itself can be also somewhat complicated as a deep learning approach. All right, so let me unpack a little bit more details about this approach as a diffusion model. Now, previously, we only looked at a single small molecule and changed the torsion angles. Now we have few other degrees of freedom to change. We changed the position and we changed the overall rotation, along with changing the torsion angles. So in learning a diffusion process, you need to define a forward process. So how to take now an actual binding pose and add noise and detach it from the correct location and orientation and shape, and ultimately get to a random version, and then learn a model to reverse that type of steps. Okay, so the way we introduce this forward process is the location is a standard Brownian motion. So you start from a binding location, actual binding pose location, and what you end up with as you add noise is just a random location around the protein. In terms of rotation, overall rotation of the molecule, you start with that correct rotation, and then you end up with a uniform sample from a uniform distribution of possible rotations. And we already talked about how to noise the samples from the hypertorus in terms of these wrapped normal distributions. All right, so this is the forward process. So how I'm going to detach, and then I'm going to learn a denoising model to generate the actual binding pose sample. All right, so there's one complication here is that as I change the torsion angles, I'm also changing the rotation a little bit, maybe translation a little bit. So I would want to disentangle these degrees of freedom. And we do that actually by aligning, after changing the torsion angles, we align the molecule back as best as possible to remove any linear or angular momentum from the torsion angle change, so as to disentangle these degrees of freedom. And the rotation is always around the center of mass of the ligand. All right. Now, how do we then predict the denoising steps? So you're given the 3D structure of the protein. You're given some random version of the ligand. It's not in the correct location, not correct orientation, and the torsion angles are a little bit off. So, but you now have a model here, what I call a score model, that takes this pair and predicts a single number here for each rotatable bond about a correction of that angle to get a little bit better shape for this molecule. You predict the rotation change, and you predict a location change for this molecule. And you can think of the protein as fixed, and the only thing that changes is the compound relative to the protein. All right. So there's not anything particular about that neural architecture. It uses tensor product networks to implement these prediction. It's more the framing and the formulation that makes a difference here. All right, so this is just an illustration of the workflow, how things work in terms of this approach. So you start, you give me a drug, 2D graph of the drug. I use an RD kit package to generate the initial configuration for that molecule, 3D configuration. What that nails is the local structures of that molecule, the local bond lengths, local bond angles, but the torsion angles are all off, okay? Now, then what we do is we sample random location, random orientation, and randomize the torsion angles. That's the noisiest version of the compound that we start with. And then successively start denoising that sample towards an actual sample of a binding pose. So you apply this score model that I talked about iteratively multiple times to take each initial noisy sample here successively towards an actual binding pose location through these iterative corrections. Okay? And once you have done that for, say, 10 or 40 samples, then you can use the confidence model to rank those actual poses relative to the protein to select the top few of them. All right, so that's the flow. So then how well does that work? So here's now an illustration of all the methods that I mentioned before, both deep learning approaches as well as search-based methods. And on the y-axis here, you see the fraction of candidates that they propose that are within 2 angstrom of the real empirically verified binding pose. Okay? Now, you can improve these search-based methods a little bit, as I mentioned earlier, by providing them some information about the binding pocket, so where to search from. So you can actually get better performance out of these by combining the deep learning approach or another pocket predictor with the search-based method. You get a better accuracy. Now, if we compare these to what we get with this geometrically guided diffusion process, then you actually get a substantial improvement over the fraction of times that you get to a very close binding pose. And compared to the previous best deep learning approach, which were comparable or below the search-based methods, then for the first time, we're actually substantially improving the accuracy of predictions.
Can I ask a question? I don't know if you can.
Please. Absolutely. Go ahead.
I'm just curious. So earlier you're saying part of the motivation, for the reasons the regression approach fails sometimes is because you have multiple locations. But I don't understand in terms of this metric. It seems like there's only one kind of ground truth. So how does that, within 2 angstroms?
The regression, you can think of it as a property of across samples. So even if you have a single example, the covariate, the protein changes, and the ligand changes, and the location changes, but overall, those examples illustrate the variability of having multiple binding modes there that the regression-based method gets confused by. So there is now a limit, as you say, I'm comparing to a single crystal structure. Ideally, I would compare to a multiple one, get the dominant binding location, but also sample some of the other ones. It's true that will limit overall accuracy here, how far you could get to, even with the distributional approach. But if there is a prominent one binding pose, then this higher performance would capture that as well. But you're right that we are limited by the empirical data here to truly test how many locations, significant binding poses there are for any particular pair.
So as a follow-up, I mean, if your generative model was like perfect and it's giving you some distribution of possible locations, you could maybe guess like what the hit you would get in terms of this particular metric would be, because you're just picking one of them. Do you have any idea like how big of a difference that might be? Does that make sense?
Well, let's put it simplistically. So let's say each compound has two prominent binding poses, and they are quite different from each other. So the top performance I would get here is 50%.
Right, that's what I mean. But I mean,
I'm predicting.
But I mean, I'm just like from the DiffDock generative model. If you took it as sort of ground truth, do you have a feel for like how much of a hit you would get? Because it's not just two equally weighted ones, it's population.
Yeah, it is a population. So this is actually an illustration. You can see that it actually generates samples that are mostly in one with and a little bit also in another location. So the confidence model that we use at the end helps mitigate that a little bit, because it's used to select the best one and compare that best one against the empirically verified structure.
Okay. I guess I'm just saying that if you took DiffDock or the generative model that's used as like ground truth, you could maybe estimate what the best you could do in this metric is, having some idea of what that population is. But I'm just curious if you know quantitatively what that might be roughly.
Yeah, I understand the idea. I don't have a quantitative answer for you in terms of
practically you're not typically going to see a ligand with multiple binding poses at very different points in the protein with similar energy. And if they're not similar in energy, then you see one of them exponentially more than the other one. So it's not actually really a practical concern of like, oh, I've got to make sure I get both binding poses, because it doesn't really happen.
Well, I mean, if it's exponentially more, then you should get close. Then it's effectively there's just one.
Yes. So I think effectively there is one. I just think we're not quite getting right.
But I thought the motivation earlier was that there's
some proteins have this
sometimes there are symmetries,
though. You have different geometry once this has bound in one place, the drug molecule, and then you have.
Oh, it does, but it's not that you have, I bind here, and now I switch around and bind over here, and now I switch around and bind over there.
Yeah, but then afterwards you have a different geometry, right? Once that you have one binding, and then that can switch, and this can be a different geometry that you're handling, right?
Yeah, but none of that is handled here, because we have one crystal structure. Yeah, I agree with you, though. Yeah.
But it depends what your reference ensemble is, right? I mean, if you compare to the crystal structure, I would agree that, if you got the ligand to bind on the other side of the protein, that's probably not a very good binding pose. But if your cutoff is 2 angstrom, and your reference would be like the 300 Kelvin ensemble, very little would fall into a 2 angstrom cutoff, right? So it really depends on how much flexibility do you allow, because 2 angstrom is like nothing at physiological temperature.
Sorry, I don't understand the point. I mean, we're not going to observe a significant population at 300 Kelvin in 2 different binding poses with the protein.
But 2 angstrom cutoff isn't 2 different binding pockets. It's just a very tiny isomerization, protein flexibility would get you out of there. So it depends what you reference also.
Oh, that's a good point. Yeah, this could be the same binding pocket. And some movement could be different, and that might be that could be relevant.
Yeah, the multiple samples that you're actually generating can be kind of concentrated around nearly the same binding location, and essentially kind of covering the energetically possible variations, assuming it worked correctly. Now, one
other sort of related question. For the 19,000 structures that you've used, are these APO structures, or they're already bound to the ligand, but you just remove the ligand and dock it back in?
I'm not sure I heard the question. Can you?
My question was, when you do the docking, do you use the structure that had bound the ligand and you just remove the ligand from it? Or do you use an APO structure that never bound the ligand?
We use the structure with the bound. That's true. There's a difference here between structures. The structure of the protein can change resulting from the binding, and that structure can be slightly different. So we take the structure. The only available data that we have here is the structure of the protein with the ligand bound. We're not in these results that I'm showing you here. We're not capturing that difference. But let me show you the next step that may get at that question a little bit. And one way to test the utility of this, which was pointed out earlier, that I do need that crystal structure of the protein as an input. So what if I don't have it? What if I only have a sequence for the protein? And I need to use a folding algorithm to generate the structure, to which I then try to dock the ligand to. How well can I solve the problem now? So can I actually get close to the true ground truth binding pose in the original verified structure by generating the protein structure with a folding algorithm and then applying the docking? So we actually did that and used ESM fold just for speed. So you, for any test protein, so none of the methods here are at all affected during training by they have not seen any ESM folded structure. So this is only for testing. So you take a protein you folded, you now have a predicted structure for the protein. You align that protein structure with the correct structure, and then compare, if you dock to a predicted structure, how well it actually matches the real one. Okay. And all the methods go down in terms of accuracy because there are some structural variations that are generated by the predicted folds. However, the gap between DiffDock and others is actually considerably increased. So the DiffDock, this diffusion model, is actually somewhat robust, in part because it doesn't use yet the side chain information from the protein structure in any real way. So it is a little bit more robust to these differences in the folds. All right, so being more accurate and more robust against generated structures, it still is at least 3 times faster than the best competing alternative here. Another advantage that I mentioned earlier is that it doesn't generate samples that have self-intersections because you're actually modeling distributionally the binding poses. You're learning to generate real binding poses. So you tend not to generate invalid 3D configurations. All right, so that's the second problem, predicting blind docking. So the last thing that I wanted to mention here, how much time I actually have at this point?
You've got about 8 minutes.
8 minutes. So very briefly, I'm going to talk about scaffold design. So how I take a known binder and design a nanobody, scaffold a known binder for it. So using diffusion-like models, but in a generative sense, realizing new protein structures. So what is the scaffolding problem in a little bit more detail? If you have, say, a native protein here, you have a binding motif here that you would want to take out, extract that, and then rescaffold it so that you get a nanobody that's therapeutically more accessible. And our task here is to generate that scaffolding structure in a way that it holds the motif in place, and this is a stable protein. The way we approach this problem is by first estimating a distribution over small protein structures. So this is just an illustration here X here, a point in the square, is a possible protein. The colors highlight the likelihood of a valid protein structure. So first, you apply a diffusion model to generate 3D backbone structures of proteins, say proteins of length from 100 to 300 residues. Okay? So you have a distribution over structures, and folding algorithms don't really solve this problem because they take a sequence and give you a one structure. I want a distribution over these 3D structures. Okay. Once we have that distribution, then we condition on the known part, the motif that I wanted to keep, and sample a scaffold by conditioning on this protein model. So if the y-axis here is the motif, x-axis or horizontal axis here is the scaffold. So you now condition on the motif, and you take a slice of this protein space and sample conditionally from this distribution. Okay. And you can vary the length of the scaffold that you want. But what we assume here is that you are giving me the length of the scaffold you want, as well as its location within the sequence relative to the motif. Okay. And my task is then to generate the full 3D structure that contains the motif and the scaffold. The challenge here is to actually learn the initial distribution over 3D protein structures. We have a new method that does that based on frame diffusion. I'm not going to talk about that. That's similar to diffusion models that we've already discussed. But some of the results that I'm going to show are actually based on the older diffusion model over the backbone structures. The other challenge here is just the conditioning. How do I take the known motif and then using this model, complicated model that has these multiple sequential denoising steps, generate one complete sample? How do I actually condition that model on the motif that I want to generate the complementing scaffold? So I'm going to focus very briefly on the conditioning task and just illustrate how we solve that very briefly. So here's the only the motif, so 3D structure of the motif that I wish to keep. I can add noise as I would normally in the diffusion process when I learn them. And ultimately, I get this kind of a random structure with some sequence ordering still present. Okay. Now, if I generated a sample from this complete protein model, I would need a random sample of the scaffolding part as well, and then successively apply this denoising model to generate both the motif and the scaffold. So here, what we do, we actually take the motif sample from the forward process and that random sample here and use the complete model to generate a scaffold, slightly less noisy version of the scaffold. So we generate samples relative to the known motif sequence. And you can continue to apply this. This is something called replacement sampling in diffusion models, and ultimately then get a scaffolding sample. Now, it doesn't work that well in our context, this basic replacement sampling. And one reason is that it doesn't actually do the right conditional. It doesn't maintain the right conditional distribution of these scaffolds. The way you can enhance that, make it actually do the correct conditioning, is to generate not a single sample here, but a bag of samples, bag of particles, and then reweight those particles by applying the same model again in terms of the ability of each of these particles in combination with the motif, noisy version of the motif, to reconstitute the less noisy version of the motif at the next step. Okay, and then you can resample those particles with these weights to get now the true posterior sample of the scaffold, and you're moving that posterior distribution towards the actual sample in this diffusion process. And you can show that if you have infinite number of particles here and your model is, your overall protein model is correct, then you're actually doing the proper conditioning. So how do I evaluate now models that generate new 3D structures of the backbone? Well, I have the known motif here. I'm going to generate a scaffold to go along with it. Now, I can use inverse sequence models, models that predict the sequence for backbone structure. I can apply that and then refold that structure. And if this is a stable 3D structure, something what we call designable structure, then this sequence back to folding actually returns essentially the same structure. Okay? So you can compare the full structures, or you can compare whether you actually maintained the motif in place that you wanted to keep intact through this predict the sequence refold steps. Okay? And we can measure how well we do conditioning by varying the length of the scaffold that we are introducing, the size of the scaffold, and seeing how well we keep the motif in place in the refolded structure. Okay. So these graphs, I'm not going to go over them in detail. I'm just going to say that this particle version that does proper conditioning actually has the ability to keep the motif in place much better than the sort of simpler versions of conditioning as you increase the size of the scaffold that you want to use to hold this motif in place. All right, so I'm basically out of time at this point. So the last thing I'm going to just say in 1 minute here is that what we've used here is ML tools to try to model molecules. You can actually essentially go the other way, use physics to inspire better models. And we've realized a new type of diffusion model, similar to a diffusion model that actually performs better than ordinary diffusion models, inspired by electrostatics. So looking at the data distribution as a charge distribution, and essentially do the same thing. You can sample from it by sampling now from a hemisphere to generate and follow the electric lines to generate a sample. Very similar to diffusion processes, but actually performs quite well, but is inspired now from physics. So with that, I'm going to just end and just highlight these other papers that I touched on very briefly. And the students and postdocs are here. The key students and postdocs are underlined here in the context of each paper. All the credit to that. And with that, I can take more questions if you have.